Well, Evan, if it's okay with you, why don't you pull up your slides and I'll just do a brief introduction. So good morning, everyone, and welcome. It's a real pleasure today to introduce Evan Kayas. And Evan, I think I pronounced that wrong, but apologies. And Evan is a geomechanics specialist at W.D. Von Gaunten Engineering in Houston. And he received his PhD in mining and earth systems engineering at Colorado School of Mines. And Evan was telling me that was in numerical modeling of coal extraction, I believe. And so in recognition of that, he also has degrees in civil engineering, an MS, and a physics bachelor's. His research interest is currently focused on plasticity and micromechanics in the laboratory. And his professional career in Houston has been focused on laboratory characterization of unconventional oil and gas lithologies. And that's been in consulting and R&D environments. And so he's also particularly interested in hydraulic fracturing and specifically in rock proppant interaction and clay stability. So great pleasure to introduce Evan.
Thank you very much, John. It's a pleasure to be here. So as my title slide indicates, I'm going to be talking today about reservoir compaction. This is an old topic that was a big deal in conventional resources and hasn't gotten a lot of attention recently because of the unconventionals focus. However, I'd like to change that a little bit. The work that we've been doing here has shown some surprising results. That compaction is occurring in unconventional mudstones associated with unconventional resources. And so I'm going to talk about that. But first, I'd like to acknowledge the fact that this is a collaborative piece of work. I couldn't do it without a lot of help from others. And so I'd like to acknowledge those who've helped me at WDVG, notably Roberto Suarez Rivera for his guidance and active participation in the work that we do here. Also, the images that you'll see here and a lot of the geological interpretation supplied by John Degenhart, resident geologist here at WDVG, and big thanks to Ryan Zach for all his help in the lab as well. And also, I'd like to thank you, ARMA. It's been a long time. I've been a member of the community for many years now, and I've learned a lot from the greats, that are part of this community. And so I'd just like to thank you all for the opportunity to share my work with you and express my gratitude. So why am I talking about plasticity in the hydraulic fracturing committee necessarily? Well, the reason being is that we typically consider mudstones for practical purposes linear elastic rocks with brittle failure. And so that most of us know that is not really the reality. In fact, we see a lot of plastic deformation and displacement associated with all parts of the life cycle of the well. And these have big impacts on the decisions we should make in terms of completions and the analysis that we do. And so I'd like to just present some simple laboratory results here that demonstrate that plasticity and talk a little bit about how this could impact decisions that we make in the field. The way that I'm going to do that is I'm going to give you a brief review of compaction plasticity from a really basic standpoint that I think it will be palatable for all. And then I'm going to talk about two mudstones that we've tested, amongst others, by the way, but two mudstones that we've tested in the laboratory that show this plastic behavior. And we'll go into a question of how is this deformation exactly occurring? And so that's where the SEM images come in that we'll talk about. So let's jump into it. All right, and so this does feel I feel a bit silly explaining triaxial testing to rock mechanics community, but of course, not everyone in rock mechanics is a practitioner in the lab necessarily, and so I thought it would be helpful to just get everybody on the same page and bring us up to speed. And so when we test a plug in a triaxial machine, I'm typically testing 2-inch by 1-inch diameter samples. You can see an example of which on the left side. I'm going to bring up my pointer here. And so typically in these compaction studies, I'm looking at laminated samples that are oriented with the axial load perpendicular to bedding. And you can see in the micro CT image, you've got some nice fabric here showing the laminations. And so during the test, we apply confining pressure signified by these red arrows. And then at the triaxial stage of the test, then we apply a constant displacement in the direction which induces an axial stress difference. And so plotting stress versus time, it looks something like this, or at the beginning of the test, we're applying our stress condition and then applying the constant displacement condition in order to generate a state of stress in the sample, which includes shear, I'll mention now. And so, of course, this is where a lot of our basic properties come from: elastic moduli, Poisson's ratio, and strength. But again, we can learn so much more from triaxial testing, of course. And so this presentation being an example of that. And so when we're talking about compaction, we're not necessarily interested in the axial displacements or radial displacements on their own. We want to talk about volumetric strain, or how the sample is deforming volumetrically as a whole. And so the way that we do this, of course, is we take a small strain approximation and we sum up the radial strains, the axial strains, to determine our volumetric strain. And I skipped over it a bit, of course, but here you have a plot showing your radial strains as the sample expands outward due to the axial deformation, and your increasing axial strain, and so providing us the volume strain. All right, and so now that we got those basics out of the way, so typically, like I was saying, typically we consider mudstones as linear elastic materials. And so what does that look like in terms of this volumetric strain? And so it's convenient for us to look at the mean stress space as sort of the average stress in the sample versus volumetric strain. This gives us an idea of, again, how the sample is deforming as a whole. And we have some images at the left that give you an idea of different stages during this compression, or during this compression test that can happen. And so at the beginning of the test, we have this nice linear elastic behavior that tends to follow a straight line. But as damage starts to accumulate in the sample, signified by these little wispy lines here, this is creating volume in the sample. And so how this manifests is that the radial strain rate starts to overcome the axial strain rate, and you actually start to increase the volume of the sample. And so what that's telling us here in terms of volumetric strain is, as we're moving to the right and positively straining volumetrically, the sample is contracting, and at this point of damage, we start to actually the volume of the sample starts to increase. And so what that looks like is this classic look of dilation that we see in the samples. Now, expected results for so we often expect to see this behavior in many samples, but what we've started to notice more and more as we look for it is something quite different. And so we wanted to start to understand that. And so I'm sort of cutting to the chase here, and I want to show you the stress strain results that sort of spurred all of this. In fact, what we're looking at is we're looking at test results from a couple different mudstones. On the left here, we have a carbonaceous mudstone from the Middle East, and on the right, we have a mudstone from the Vaca Muerta formation in South America, and a couple of samples for each, one of which exhibits the behavior that I was just referring to, a nice linear elastic loading with a dilation. In both cases, however, with select samples, we actually start to observe something quite different, where we see an onset of accelerated contraction or compaction in the sample. That's in relation to this line linear elastic behavior that's represented by this dotted line here. So this is sort of a characteristic curve or behavior that seems to be occurring in different samples from different locations of seemingly different lithologies and types. And so what is it about this behavior and that's happening on the micromechanical level, and what more can we learn by looking more closely at the micromechanics? And so what we need to do actually is we need to kind of take a step back and realize that we've actually seen this behavior before. We've seen this behavior in sandstones and limestones in the literature. And a really good example is a large body of work that's been provided by practitioners such as T.F. Wong and colleagues. Big acknowledgement to the work that they have done in furthering our understanding of compaction. And specifically, some of the work that's been done has been focused on Indiana limestone. And so what you'll notice by looking at this figure here is maybe you're catching on to the compaction behavior that's occurring in several of the samples here, because what we're looking at is a series of triaxial tests that were done at different confining pressures. So you see 5 MPa, 10 MPa, and increasing. This behavior, as I said, is referenced against what we call the hydrostatic behavior. The hydrostatic behavior is essentially compaction of the sample under hydrostatic stress alone. That is sort of our baseline deformation that we're going to be comparing our triaxial data to determine whether something's compacting or not. And so you can see that behavior highlighted here with the red dashed line, where all the deformation up to that point is what's being considered as elastic behavior, and anything to the right is that contracting compaction plasticity that I'm referring to. And so as confining pressure increases, you see this nice transition from brittle behavior with dilation to plasticity compaction, also with dilation. And so what we'd like to do is use this understanding of Indiana limestone to try to reference the laboratory results that we see in the mudstones and compare the mechanisms and try to understand better what's going on exactly. And so a good idea is to think about what kind of damage mechanisms might be occurring on the micro level. And so this slide just gives you a small taste of the different mechanisms that can occur in grains and some of the damage that we might see in the sample looking forward, looking at a smaller scale. And so one of the big factors is of course the coordination number, and I'm showing the effect of the coordination number here. So as you increase the number of point contacts on a grain, it sort of changes the response of that grain to the stress. Point contacts causing fractures. As they increase in number, you can actually build strength of the grain and change the morphology of the damage that occurs. Elongated grains might experience a 3-point bending stress of sorts due to the contact of other grains. And since we're talking about Indiana limestone here, one of the things that came up was this idea of crystal plasticity. Carbonate minerals are prevalent within mudstones, and so we wanted to take a look at the mechanisms associated with calcite itself. And one of those is the idea of crystal plasticity or twinning. And so a ton of work has been done on twinning in calcite, pure calcite itself, and also in carbonate rocks, such as Indiana limestone. And so this is a strain energy dissipation mechanism that results in the visible appearance of this essentially a dislocation of the crystal lattice structure within these different grains. These can be oriented. These are oriented preferentially with the crystal structure within each of the grains. You can see on the right here, we have some nice images, cross-polar images of different carbonate rocks. And so the amount of energy that can be dissipated through this mechanism should be considered in our research here. And so the first thing that we wanted to do is reproduce the results that we've seen in the literature on a series of Indiana limestone tests. And so the way that we did this is we conducted a series of triaxial tests with different confining pressures on similar Indiana limestone samples and put those against the backdrop of a hydrostatic test. And not surprisingly, we were able to observe a similar behavior as shown in the previous figure from the publication of Vadova et al. And what you're seeing a nice brittle to ductile transition as the confining pressure increases, with an increasing amount of plasticity with increasing confining pressure as well. And so a really nice thing to be able to do is to visualize this deformation for yourself with your own eyes. And because of the amount of deformation that's occurring in these samples, you're actually able to do that. If you take a look at the samples that have been tested post-test, you can actually see the amount of permanent deformation that's occurred in each of these samples. And another thing to note here is, in fact, the amount of barreling that you're able to see in these samples as the confining pressure increased. This is a very real, I'll just sort of tangent onto the barrel effect for just a moment. The effect of the barreling in the test is quite palpable. You can imagine then the way that we calculate volume strains is quite affected, is idealistic in comparison to the actual real deformation that you're seeing in the triaxial frame. We have some work that I'm not presenting here that touches on that a little bit. But so what is it exactly that's going on within the sample when this deformation occurs? Well, we turn to SEM imagery to try to understand the mechanisms in each of these rocks to see if we can see any similarities. And so our base case here is that of the well-studied Indiana limestone. And so what you're looking at here on this image are two SEM images at quite large resolution, 250 micrometers, in order to capture the fabric of these rocks. And we're looking at them in a ion milled surface. So this is an ultra flat polished surface in two states. On the left side, you're looking at an undeformed sample. So sort of this is the as received fabric of the rock. And then one of the samples after testing, you can the damaged state of the sample. And so a lot of interesting things are here to note. You can obviously see the presence of these very large grains that we call allochems, large macropores that are lined with calcite crystals. We have micrite cement between the allochems, and you'll also notice a ton of microporosity within the grains themselves and in the cement lining the allochems. This provides a lot of volume to facilitate the compaction of the sample. And so when we look at the deformed sample, you can see the effects of that strain, in fact. Of course, we're not looking at the exact same image pre and post. That would be very difficult to try to capture, but we have some idea of what's happening, for example, to the microporosity crushing between the micrite, between the grains and the allochems themselves, crushing within the microporosity within the grains themselves, crushing of macropores as well. And so obviously a easily observed compaction behavior occurring by viewing these two images. And so another helpful thing to do is to be able to look at a different perspective of this damage. And so one way we did this is by taking a look at the rough surfaces of the samples pre and post test. And this sort of gives you a three-dimensional perspective on the damage that's occurring and also the fabric in the sample. And so the image in the top left shows this undeformed state of the Indiana limestone. Again, you have this large allochem that is coated in this microporous cement. You have macropores between the grains and also the micrite cement between them as well. You can see the small crystals lining the macropores as we increase in. So then as we take a look at the deformed samples, you can see how the damage is manifested throughout this fabric. You can see fractures propagating through grains themselves, right, through the micrite. You can see crushing of the micrite cement as you increase the resolution of the image. Even further, we can take a look at individual grains themselves that exhibit very interesting deformation. It's not confirmed, but what this looks like is it could be evidence of calcite twinning within an individual grain, as facilitated by the point load contact at the end of this grain. And so again, the damage in the sample is all too obvious. And so how is this information going to help us learn about the deformation that's occurring in mudstones then? Well, let's first take a look at the samples that are in question. So each of these next couple slides, they talk about the two mudstones that we studied. These lithologies do contain some variability, and so what I'm doing here is I'm contrasting two types of samples. Two samples that are prone to compaction against the backdrop of one sample that behaves more in that traditional linear elastic manner. And so you can see from the visible images and the micro CTs similarity between these compaction prone samples and the laminations that are present within them. Here you can see in the mineralogy of each of the samples, the sample A, or linear elastic rock, is heavily carbonate, whereas and low in total organic content. The dots are sized by total organic content here, and increasing clay content and also porosity in the samples B and C. So you can see the differences here. We have a nice clustering porosity and density on our compaction prone samples, and then our higher density, lower compaction sample to the right there. And so the stress strain results, hopefully that you're familiar with looking at this point, you can see the dilation, almost linear elastic behavior that's occurring in the sample A, whereas compaction obviously occurring in both vertical and horizontal samples. That's very hard to deny. You can see a nice contrast of the stiffness of these samples from these hydrostatic trends that are also shown in the figure. And taking a similar look at the Middle Eastern carbonate, we have two samples that are prone to compaction, we'll say, and one that is not. The interesting thing about this set of samples here is that this carbonate rock is almost entirely carbonate, and so it's not necessarily the mineralogy itself that's defining the behavior of these samples. Of course, we do have more organic content in the samples EF, and however, and you can see also the layering present in each of the samples as well. And so there's a lot of factors at play here, of course, mineralogy, organic content, fabric, that are all playing into this behavior. And so you can see on the right, we have the results for each of the samples shown. You can see in the two, an extreme amount of compaction occurring in these samples with the purple lines, and sort of this more linear elastic dilation with dilation failure in the other sample. And so then let's take a look at what the fabric of these samples looks like pre and post test, and see if we can contrast any of the damage mechanisms that we've learned about in Indiana limestone with the mudstones that we're looking to. And so here's an image of a mosaics of two both of the mudstones. You have the Vaca Muerta sample on the left, and the mudstone from the Middle East on the right. And the first thing you'll notice, because of the scale here, we've actually got a very similar scale to what we were looking at with the Indiana limestone. And so what you'll note is that we have a much finer grained material here. In fact, one of those allochems in the Indiana limestone would probably take up nearly almost the entire image here. And so a big contrast in terms of the rock that we're looking at. But mind you, we're still seeing the same behavior in this in terms of compaction and what it looks like in terms of stress strain. And so again, just mentioning that, so harping on this idea of what are the differences then? If they look same in stress strain behavior, how do they appear different in terms of their damage? And so taking a look at a closer look at the Vaca Muerta sample, you can see a lot of silicate minerals. There are elongated feldspathic grains here shown here at I, and also this undeniable behemoth of a grain here. And in comparison to the Saudi mudstone, we're looking at larger dolomitic euhedral crystals, along with more amorphous calcite and smaller calcite minerals. But in both cases, these are all set against the backdrop of this darker organic material. And so let's see, to get an idea of how both of the damage manifested in each of these samples, we'll take a look at both of those close up. So first, the Vaca Muerta sample. The remarkable thing about the Vaca Muerta sample is that it really wasn't apparent the damage mechanism in the sample. It was actually quite difficult to find the damage. That's why on the left side of the screen here, I'm highlighting a very small window of that previous image to show some of the damage that was obvious in the sample. So throughout this grain, we have a fracture that propagated through it, have a dislocation event, and also some micro cracking that occurred here. And so, like I said, notably though, the rest of the sample seemed largely intact. In fact, when we talked a little bit before about 3-point bending, at these grain contacts, we see very little. You might expect to see these elongated grains exhibiting tensile fractures. Those didn't seem to be present. We don't have a lot of grain crushing at contacts. And so only when you look very closely in some of the rough surface images do you start to see fractures and the complex nature of the fabric. But again, no clear mechanism for the deformation. And then, of course, taking a close look, though, when you see in the image at the bottom right, what we're seeing here is essentially a humongous collection of biogenic calcite in the form of these coccolithophores. And so if we take a closer look at those, one possible mechanism for the compaction of this sample could be lying within all of the void space and porosity that occurs within and around these coccolithophores. And so this is, of course, masked by the damaged state of these little critters themselves. And so any damage that occurs in the sample, it would be really hard to parse out from that which occurs during deposition. All right, and so you know, moving on then to the mudstone from the Middle East, we saw a little bit of a different story. When we take a look closer at the grains and the damage sample, we start to see the manifestation of that stress very clearly. You can see in these blue arrows a lot of fractures occurring within those dolomite grains themselves, mainly along preferential planes. Taking a closer look, you see complicated behavior that's associated with shear stress, and also at grain contacts and large grain contacts at that, we see a lot of crushing. This crushing, and so typically, a point contact creates a large stress concentration, whereas a long contact would distribute that stress more efficiently. And seeing the crushing at those distributed boundaries is strong evidence of the amount of stress that was in the sample. And so, of course, we do see a lot of damage within the sample post-test. However, a nice way to look at it is that with these rough images, you can get a three-dimensional perspective on those fractures that are propagating through the dolomite grains. You can see nice examples here, examples of tortuous fractures created by shear stress, some spalling at the grain surfaces, individual grain crushing, and so we do see a lot of damage in the sample. Yet the amount of volume strain that we were seeing during these tests was on the order of 3-4%. It seemed that some fractures propagating might not fully explain it. And so when we take a closer look at the organic material within this mudstone, we start to see something very compelling. And so in this image, what I'm showing you is on the left side, I'm showing you undeformed sample, so prior to testing, and then the rock fabric after testing on the right. And so what we have is a large mosaic with 3 locations within that mosaic here denoted by these red boxes. And prior to testing, you'll notice that there's a pretty consistent pore size distribution all throughout the image here. You can see that in each of these images, you have nice large pores. Following the deformation of the sample, you can see a clear decrease in the volume of these pores. And so by taking a look at different locations in the mosaic, we can see that this is definitely not a localized phenomenon, but very very compelling reason for the compaction that we're seeing. And so what does this behavior necessarily mean for hydraulic fracturing and oil production in general? So of course, I think most of us have a pretty good idea of this, but this slide gives us a very clear idea of what plasticity at fracture tips could do to fracture geometries. So here we're looking at a simple finite element model. In each case, we have a fracture with the same amount of pressure in it, same geometry, only we're simulating more and more plasticity as we go from left to right. And what you'll notice are 2 things. You'll notice that the stress concentration created at this tip is more largely distributed spatially. And so the plastic deformation that's occurring at the fracture tip is actually blunting the fracture tip and reducing that stress concentration. And not only and through that, the stress that occurs at the fracture tip itself is also decreasing. And so this, of course, would manifest itself in larger widths in fractures and perhaps in reduced height growth as well. And so, of course, assuming linear elasticity for materials, for our geomaterials would also be a problem in the case of something like wellbore stability. Nonlinear behavior has a big impact on borehole stability, in fact. And so the way we can understand this is by taking a look at wellbore stresses in both cases. And on the left side here, you're looking at Young's modulus versus the confining pressure. And so in a typical linear elastic case, you see that the Young's modulus is consistent for all confining pressures, whereas oftentimes more realistically, the Young's modulus is changing with confining pressure. And so this shows up the stresses that manifest from these different models, if you will, is very different. In the case of linear elasticity, we see a strong peak stress right at the wellbore surface, which usually results in the understanding of what we see as breakouts in the wellbore, and then that stress declines moving away. But in the case where you have nonlinear elasticity, the peak stress the peak stress actually occurs at some distance away from the wellbore surface, and in fact, this results in a slightly lower stress in this case. And so what this serves as is essentially a wellbore strengthening effect. And so if we take a look at, just considering some reasonable numbers for the strength and properties here, if we look at the drawdown pressure required in order to fail the rock at the wellbore surface, or at the wellbore, in the two different cases, we see the improvement in this case that's shown with considering the linear elastic model of the rock, where with linear elasticity, the well is drawn down 2000 psi, and you can see at the wellbore surface the stress state has touched this failure surface. Whereas in the nonlinear case, you can achieve, in fact, so each one of these lines here is showing showing the drawdown stress. So we can achieve an additional 1800 psi of drawdown before the stress reaches the failure envelope. So a big difference, and by not considering this nonlinear elastic behavior, we're certainly doing a disservice to our understanding of the situation. And so where is it that we're taking this work? It's one of the things that we've been looking at then is we want to consider how this plasticity can be used in analysis of situations like wellbore stability, for example. And so one of the things that we've done is we have formulated a constitutive model based on the laboratory results from the Vaca Muerta mudstone. And here, what we're doing is the constitutive model uses a modified cam clay model, which is this elliptical failure envelope constrained by the critical state line, and the data of reduction in pore volume and how the hardening behavior occurs comes from the Vaca Muerta data itself, notably during these hydrostatic cycles that we do prior to the triaxial stage. And so this constitutive model was formulated. It was tested at a Gauss point level, and in the model was able to fairly well reproduce the plasticity that's seen in the samples that we tested in the laboratory. So, of course, this is the beginnings of this work, and we hope to build on it in the future. And so I'll close up with just a few comments. I think I've mentioned it a few times, but in terms of analysis and in practice, we typically think of mudstones as being these linear elastic materials. And it's obvious to us in the laboratory that we see that it is not the case. And we do ourselves a disservice by ignoring these nonlinear behaviors and plastic deformations that could lead to erroneous conclusions on fracture geometries or stability in wellbores, for example. And so it's important to note one of the enlightening things here was that while the stress strain behavior looks similar between these different rocks, for example, the mean stress volume strain curves in the Indiana limestone look quite similar and characteristic to those of this carbonate mud rock from the Middle East. There's very different things going on inside. And so it behooves us to try to understand the micromechanics of that deformation and further then to maybe understand what implications it might have for things like production, because we did see in the case of the Middle Eastern carbonate, a lot of compaction in the organic material. So what does that mean in terms of permeability and production? And so this, of course, is a challenge, trying to understand the micromechanics of each of these rocks and how they vary. And so I continue to seek ways to try to improve ways of visualizing this damage and quantifying it. So I'll finish things up there, and thank you very much for your attention.
And thank you, Evan. Very, very, very provocative, and it's a topic that we don't often consider. It does have relevance, and you have generated some questions. The first question was from Colin Sayers. Colin is observing that the barreling implies friction at the interface between the sample and the platens. And he's wondering, from a laboratory perspective, what steps do you take to reduce this, and how does it affect the results?
Well, steps that can be taken, of course. Some lubricants have been used in the past. Typically, this, of course, as you're saying, the effect is palpable. And like I was saying before, let me go back to that image. Sorry, I'm having trouble getting to that. The image of the barreling. It harkens to our assumptions of what the volume strain is in the sample. And so in the case where barreling is occurring in these extreme cases of confining pressure, yeah, the volume strain that we're going to report by assuming that the sample is deforming cylindrically are going to overestimate the volume strain. And so this changes our quantification of how much volume strain is actually occurring.
Very good. And Brian Gilmore, Brian's asking, what steps do you take either during sample prep or testing to eliminate or separate the effects of damage and fractures resulting from plug extraction from recovery?
Well, there's not much you can do, Brian. And so that's why we put a lot of effort actually into just sample quality itself. And so when you look at when you were looking at some of the micro CT images that I was showing you for some of the samples, we're able to screen out samples with fractures or obvious damage. And the QA/QC doesn't really end there. Of course, we have a lot of sanity checks that go along during testing regarding the redundance of velocities in vertical samples, and also the redundancy of bulk modulus within horizontal and vertical samples that allow us to quality control the data and ensure that our samples are self-similar and that we're not getting an outsized effect of extraction. Because of course, we're bringing this core up from thousands of feet under the ground. There's inevitably going to be some changes that occur. The best thing that we can do is work to minimize those, screen out those samples that are problematic, and ensure that our data is consistent.
Very good. Now, Ed Sieberts has got a slightly different question. He's wondering about acoustic velocities in the lab as a diagnostic for what's going on. What is the effect of higher confinement and compaction and dilation on ultrasonic velocities?
That's an interesting question, Ed. I have to admit I haven't looked deeply into that question. Of course, the velocity as the test progresses, the density of the sample is increasing, and with the increase in density, we see an increase in velocity. However, you do see changes in this when the sample starts to dilate and your density goes down. And so the I would say then that without looking at very specific or cases, you can pretty much assume that the velocities are going to trend along with the density, and that density is going to trend along with the volumetric changes that are happening in the sample. I hope that touches your question.
And now Javed Iqbal wants to make the situation a little more complicated, and he's indicating that if we're treating with a cold fracturing fluid, that fluid interacts with hotter rock at the matrix fracture interface, and that the mean stress at each grain reduces and contraction happens. He wants to know if you've done anything in your lab test to consider this.
When cold fluid interacts with hot rock at the matrix, the mean stress at each grain reduces and grain size contraction happens. Can you outline? Oh, so you're talking about damage that occurs due to changes in temperature. And design of your lab tests aim at minimizing the effect. Well, so we of course in the laboratory our aim is to control all the variables that we can. And one of the things that we do is we're essentially controlling the variable of temperature by testing everything at ambient conditions. And so we are in most cases, we're not looking at the effect of especially low temperature on samples. And however, it's a very interesting question. This is something that you wanted to investigate, the damage that would occur to samples before and after being exposed to these types of temperatures. You can easily see a testing program that you could design around that. And of course, you just do your best to make sure that all of your procedure is consistent, and you're not introducing unwanted variables. And so again, like I said, we're not minimizing the effect because we don't allow the effect to occur in the first place.
Next, Hector Gonzalez has an interesting question, and he would like you to comment on the influence of stress path for calibrating your CAM-clay model. And also whether or not, I mean, presumably your tests are being run drained to atmosphere, and whether or not undrained or drained testing condition would be appropriate.
Okay, I'm sorry. I was reading Ed's.
Oh no, Ed already answered his own question.
I see that. And I'm sorry. So do you think the undrained condition is relevant to this type of formation? Of course, this is actually something that I'm actively thinking about. We've been looking at drained versus undrained conditions just yesterday. I was thinking about a few moments ago, and this is in reference to porosity, right? And the fluid motion within the sample. If you're looking at a sample like Indiana limestone, the permeability is quite high. Of course, there'll be an effect of I'm sorry, I lost my train of thought here, because it all has to do with the permeability. The type of formation that you're referring to, I assume, are mudstones. Mudstones have very low permeability. And so, of course, the undrained condition would be relevant. We test typically test samples under the as received condition. And that's under the assumption that the sample is not 100% saturated. And so when the sample is not, and you may know, based on how you're asking me this question, you may know that saturation is very important. If you don't have your sample perfectly saturated, you're not going to get the right poroelastic response out of the sample. And so, in the case of mudstones that are in situ condition, aka perfectly saturated, of course, the undrained condition is relevant because the time scale at which it will take fluid pressures to dissipate is high in reference to the strain rate. And so this is something we're actively looking at, and I really appreciate your question.
Very good. Now, Eric Schmelzel, Eric's question, well, and you can read it, but I'll just read it out loud for people, is he's wondering if you've tested samples that have more extreme microlamination and bedding planes, and if you have any insights on those.
I think you mean when you say microlamination, you're referring to the laminations that you saw in the CT image. Of course, we test a lot of mudstones here. We test and bedding is an important word around here because, of course, our samples have to be properly oriented. If they're not, that affects your results. We're looking at mechanical properties with respect to the bedding, and so it's very important that we consider the bedding in all of our tests. And so, of course, then what is the effect? The effect is well known. We understand well how bedding affects mechanical properties in parallel and perpendicular, and so. Yes, I encourage you to, yeah, there's a lot of information in the literature about that. But I don't know if microlaminations is what you mean, are the laminations that I showed you in the image, but high degree, and you don't mean like 45-degree sample or orientations with respect, different orientations with respect to the bedding, do you? Because of course, and I guess in a less verbose way, I should just say, of course, we do consider the bedding, and it has a big effect.
So there's a good answer. Yeah.
Yeah, and I don't know if I should say that, but specifically, if I'm overlooking the obvious answers, you're going to see lower stiffness perpendicular to bedding and higher stiffness parallel to bedding.
And then the next observation is from Mohammed Azamuddin, and he's indicating that you can map the profile of the strain by using multiple strain gauges or circumferential strain measurement at different, slightly off-center locations. Maybe you want to comment on that, Evan.
Yes, thank you. I mean, thank you for making that comment. It's definitely true. The rock fabric can be complex, and being able to capture the uniformity of deformation is important, and that's one way you can do it, is you can use multiple cantilever gauges, multiple strain gauges, a chain gauge of sufficient design. So thank you. Yes.
Wei has a number of questions. He's interested in the confining pressure and loading rate and water content. And is there evidence of pore collapse during the elastic phase?
I don't know. I seem to be getting a lot of questions about the mechanics of testing, which I really enjoy. I enjoy these questions. I'll talk about them all day long. I'm wondering.
So let's skip to the next.
So what I would encourage anyone to do is, like, please know that I'm open to your questions. If anybody wants to know some more details about testing, I'm happy to take your emails, and so feel free. I don't get all those questions answered, but here, touching on your question here, comment on the definition of compaction versus early stage of such tests when microcracks close under loading. These are very different portions of the test, and so this is also well understood. We have so you'll even see a little bit of it in this slide here. If I don't know, I think you're still seeing my pointer, right? You can see sort of a foot on this on this curve at the beginning of the test. Closure of micro cracks is sort of the first stage of the test. And in fact, you can do things to mitigate the presence of these cracks by, say, performing a few hydrostatic samples before the triaxial stage is one way to accomplish that. And that's in fact what we did in with the Vaca Muerta samples in preparation for creating the constitutive model. That those hydrostatic cycles allowed us to see how the pores are changing. And the difference being between when pores are closing, are consolidating under stress that they haven't seen before, and then unloading and in a topic well used in soil mechanics, that you have sort of unconsolidated versus consolidated deformation. This is all very different from that initial portion of the test where you're just closing microcracks, sort of a necessary evil that you just need to go through in order to get try to restore the sample to its in situ condition and test the properties that you want to test.
Yeah, and so let me just follow up on that. That if you have specific testing questions, don't hesitate to reach out to Evan, or if need be, I can forward messages. But Evan, just as you mentioned, we do have two final questions that sort of hone in on practical aspects of this outside of the laboratory testing, and from Ali Danishi and Colin Sayers. And Ali's question is, what do you think about the effect of compaction on production in these reservoirs?
What do I think about production?
The effect of compaction on production.
Oh, okay. I have lots of thoughts, of course. I'm just a guy studying these things, and I'm learning as I go as well. I'm definitely not an expert on permeability and on oil production, but with the things that I have seen is that the compaction that we see in other words, the shear enhanced compaction that we see in these samples has a big impact on the pore pressure in the sample. In fact, we see in some cases, we see much greater increase in pore pressure with during the triaxial stage, where you're applying a constant boundary condition, than you do in a hydrostatic state. And so what that means is that you're affecting your pore space differently. You can think of it as kind of like kneading a piece of dough versus just squeezing it all around. And so the changes in the geometry of this pore volume could have a big impact. Does it close? Does it reduce production? Or does it enhance production? That's something that I personally am not sure of yet. I imagine in some cases, yes, in some cases the former, some cases the latter. And the reason I say that is because what we saw in these different samples, for example, the Vaca Muerta and this mudstone from the Middle East, is that the mechanisms of deformation are potentially very different. And so the response that you might get in terms of production could also be very different. And that just necessitates a lot more testing and trying to understand these things more.
Yeah, thank you for that answer. That's pretty insightful. And then I think we've got time for one last question from Colin.
Yeah.
And he's going back to Ed Siebert's question about velocities. He's arguing that it would be interesting to study PNS wave velocity measurements, since there is a competition between pore closing and microcracks forming and propagating. So
Yeah.
pore collapse would increase velocity, but microcracks would decrease it.
Yes. Okay, that's fantastic. I agree with you, because I mean, and that's one of the things that that Roberto talks about a lot. Is we talk about when we're testing these rocks, we're constantly changing the rock into something new. We're creating microcracks, and we're also closing pores, for example. And so you only in these very special cases, like I was telling you about, these linear elastic rocks, these so-called linear elastic rocks, you unload the sample and you see the same behavior that you saw loading it. That doesn't happen. And so thank you for mentioning that, because I haven't thought enough about using the velocities as sort of a microscope to look into this competition between pore collapse and microcrack formation. Thank you.
Yeah, very nice. I think just in the interest of time, we have to call it there. We've Mohammed, I'm sorry, we ran out of time. But don't hesitate to pass your question on to Evan separately.
Yeah, and I see
Well,
your
I can relay it if appropriate. But anyways, Evan, really a fantastic and insightful and provocative talk, and thank you so much.
No, thank you. Thank you all for the opportunity. I really appreciate your attention.
Yeah. Thanks everyone for joining.
Have a great day. Hey, John.